One of the fundamental skills addressed in AP Physics is uncertainty. Uncertainty is the error of measurement presented with the measurement. In other words, it indicates significance. Oftentimes, significance is measured directly from the measured value. If left unlisted, it's not often clear what the uncertainty is, and that would be when you apply the significance rules. However, when you start to do actual experiments where the precision of the various devices varies, it's very important to list your measurements with uncertainties so that that precision can be reported. Generally, this would look in a more general format. You would take the actual measurement that you've used your device to do. You would indicate it as a plus or minus and then tack the error on at the end. So a typical example would be something like 8.0 plus or minus 0.1 meters. If left unlisted, as I mentioned, since you are going to look at it as significance values, then if you were just given, for example, just 8 meters from above, right, 8.0 meters, then you would look at this 0 and know that this was your most significant value, indicating the highest precision. From here, you would indicate that using your sig-dig rules, the most precise value will then be plus or minus 1, right? Whatever the units of your particular precision value are. So in this example, it's plus or minus 0.1 meters. It's important to look out. Occasionally, depending on the device, you will see error measurements that are not multiples of 1, right, which is why they're often listed. And so, and sometimes you will see half values used as measurements. In other words, an example would be 8 meters, 8.0 meters, plus or minus 0.5 meters, right? And so in this case, it's important to recognize that you would scale by multiples of 0.5 as opposed to multiples of 1. Right? So if it's unlisted, it will always be multiples of 1 of the most precise point. If it is listed, it can exist as other values besides single digits of a significant placeholder. There are two basic applications for uncertainty that really matter for this course and for moving forward, right? And so we'll talk about those in turn. The first application is a measurement of percent uncertainty. And it's most easily demonstrated by looking at an example. So this is problem number 6 from chapter 1 on the fundamentals. The problem presents you with a measurement of 3.76 plus or minus 0.25 meters. And then they ask you to calculate the percent uncertainty. Percent uncertainty really is a matter of just how much this is in proportion to the original measurement, right? So a uncertainty percentage of the overall value. And so in generic terms, percent uncertainty is going to be the uncertainty, keeping in mind that the uncertainty is plus or minus this value. We're going to do the absolute value of the uncertainty divided by the measurement. And then we're going to multiply that proportion times 100. This will yield a percent value. The example here, of course, gives us a percent uncertainty from number 6 as 0.25 absolute value divided by 3.76 times 100 equals 6.6%. Another way to think about this is the percent error, which is another way that you're approaching displaying your precision in a particular measurement or calculation. Right? That's the first application. The second application is compounded error or uncertainty. Compounded error or uncertainty is when you have the error, the uncertainty, built into a particular variable, but then you're going to use that variable to calculate another term, and you need to carry that measurement through. You need to carry the error measurement through the calculation. What you can imagine is that if I knew what the radius of a particular device was, let's say that the radius of a particular circular object is 3.8 times 10 to the fourth plus or minus 0.1 centimeters, right? If we're going to calculate anything using that radius, so area as pi r squared or volume as 4/3 pi r cubed, when you carry this radius through these calculations, you are going to multiply the radius, but you're also going to multiply the error. And if you imagine that these are decimals, right, when I multiply a decimal times a decimal, that's going to indicate an error that is less than the original value, which doesn't make any sense. Every time I'm doing a calculation and applying a value with uncertainty to a formula, I would expect the error to compound, as in to increase throughout the system, right? And so this requires a little bit more in terms of planning and thought for my compounded error. The steps are pretty easy if we break it down, right? We're going to do step number 1, which is calculate all possible range values, right? Those range values, of course, would be the actual measurement with no error, the minimum measurement, which would be this minus 0.01, and then the maximum measurement, which would be this plus 0.01. So you've got a min, you've got a specific measurement, which ignores the error, and then you've got a max value. And so in each case, you're going to calculate the total for each one of those. So the min will be the measurement minus the low end error. The specific will just be using the calculation of the measurement, right? Just the measurement. And then the max, of course, will be the opposite, which is the measurement plus the error. So in this particular example, in order to calculate the various values, right, we're going to use our specific would be 3.8 times 10 to the fourth. The minimum value would be 3.7 times 10 to the fourth, and the maximum value would be 3.9 times 10 to the fourth centimeters in each case. Once you've calculated the values, second step is half the differences of the extremes. In other words, you're going to average these two values, right? Half the difference of the extremes. To write that in mathematical terms, we would say that the change is a measurement of the maximum value minus the minimum value divided by 2. That's going to be our uncertainty for the new calculation. Once you have that, right, then it's just a matter of reporting your values. So you're going to list the specific calculation, right, which was a measurement where we ignored any of the error. We're going to list the specific value, which would be the measurement without any error, and then we're going to add on this calculated change as our new uncertainty. So, in keeping with the radius that we have above, a typical question would be, what is the area of this circular object with radius of 3.8 times 10 to the fourth plus or minus 0.1 centimeters. So, of course, the first thing we're going to do is calculate the max, min, and specific values of the area using the various measurements of the radius. So the area minimum will be pi times the minimum value of the r, which would be 3.7 times 10 to the fourth squared. If I do that, I believe I get 4.30 times 10 to the ninth centimeter squared. If I calculate the specific value, I'm going to use the actual measurement of the radius in my calculation. So pi times 3.8 times 10 to the fourth squared, which yields a value of 4.5 times 10 to the ninth centimeter squared. And of course, finally, the maximum is going to be pi times 3.9 times 10 to the fourth squared, which I believe gets us 4.78 times 10 to the ninth centimeter squared. Notice that in the minimum and the maximum, I've carried it out to an extra decimal. This is because I don't want to over-round preemptively, right? I'm not going to round to the proper significance until I report my specific value, because I'm using these two to perform a secondary calculation. I'm going to drag out an extra significant digit so I don't over-round. So when I move on to the delta calculation, I'm going to take the maximum value of the area, A max minus A min, divided by 2 in order to get the uncertainty that I have for my new calculation. So if I do that, I have 4.78 minus 4.30 divided by 2, and I get a value of approximately 0.24 times 10 to the ninth centimeter squared. And then, of course, I need to apply my significance rules, and if you'll notice, if I had rounded these, that would have moved this to 0.3 and therefore increased my error before I was ready. And so if I round this now appropriately, my answer is 0.2 for my error. So my final measurement for the area of a circular object with a radius of 3.8 times 10 to the fourth plus or minus 0.1 centimeters would be an area of the specific value, 4.5 times 10 to the ninth plus or minus 0.2 centimeters squared. Sorry for running out of room there. Putting the two applications together, we can look at another example. This is problem number 11 from chapter 1. It says, what is the percent uncertainty in the volume of a sphere whose radius is 2.86 plus or minus 0.09 meters? So going through the process, we need to calculate each value of the max, min, and specific using the volume formula, which is 4/3 pi r cubed. The maximum value is going to be 2.86 plus 0.09. The minimum value is going to be 2.86 minus 0.09, and of course the specific value ignores the uncertainty for the time being. Running those calculations, I've calculated the specific value as 9.80 times 10 to the first meters cubed. I've calculated the min value as 8.903 times 10 to the first meters cubed, and I've got the maximum value as 10.754 times 10 to the first meters cubed.
Again, notice that I've taken extra significant digits in the minimum and maximum value so as to not preemptively round and increase my error. The calculation, of course, is delta equal to the max minus the min divided by 2, or the average of those. And so if I take that, I get a value of 10.754 minus 8.903 divided by 2 gives me approximately delta volume in this case as 0.926 times 10 to the first meters cubed. So I'm going to report my specific value, right, the final measurement of the volume, as being equal to the specific value I calculated above with proper significance based on the rules from the radius. So I've got 3 significant digits of 9.80 plus or minus 3 significant digits here of 0.926 times 10 to the first meters cubed. It's not incorrect to list this as exponential only here, with this being all strung together, but it's also not a bad idea to list it as well as 9.80 times 10 to the first plus or minus 0.926 times 10 to the first meters cubed, so that we don't make any mistakes in understanding where these things are rounded. This, of course, is just the specific value. So in order to finish the problem, remember that we were asked for percent uncertainty. And so now we know the new uncertainty. We've calculated that as our change, and we have our specific value. So the percent uncertainty, of course, is simply the 0.926 times 10 to the first divided by 9.80 times 10 to the first times 100, which comes out to be approximately 9.4%. 9.42%.